So next section is the conservation of energy. It says, what is the law of conservation of energy? Energy cannot be created or destroyed. The total input energy is equal to the total output energy. Next one, we've got an object being raised into the air and it's gained 4,500 of GPE. So we know GPE equals mgh. G was terrible there. That's GPE divided by mgh. It tells us the mass there, so that's the mass. Doesn't tell us gravity, but it's going to be on Earth, so we just need to know that that number's 10. And it says, what is the height? So we can see there, h. So if we're given the formula, GPE equals mgh, I want h, so that g, at the moment it's multiplied by m and g. That's got to live under here. Okay, so, sorry, that's my board beeping. So we now know h equals GPE over m times g. Pull down our 4,500. It's in joules, so I don't need to change it. This is in kilograms, don't need to change it. Multiplied by 10, that's the gravitational field strength on Earth, and I get 8.2 meters. Next part, water within a dam gains 1.2 kilojoules. Okay, so that's 1,200 joules. I'm going to change that there. This drops through a water generator and transfers 850 of useful kinetic energy. The rest is wasted. What is the value of the total wasted? Well, we know that total input equals useful plus wasted. So if we take the 850 from the 1,200, we're left with our wasted energy. It says, what and where is the wasted energy transferred to? Well, this is in a water generator, and in the generator there's going to be friction. So as a general rule, you're always just going to talk the waste energy is thermal energy, and it gets dissipated into the air, and you're going to be sick of how many times you have to use that. So thermal energy from friction is dissipated into the air. And our last question in this section, I think, let me just quickly check. Oh no, there's a few more energy ones. So we're going to need efficient, useful tools. And it says it transfers 520 of electrical energy. So that's the input. So I'm going to put that's the total input. 0.12 kilojoules. So that's 120 joules is wasted. And it wants the efficiency. So the important part is we're going to have to take the 120 away from the 520. I need the useful, because we know efficiency equals useful over total. I've got the total, but I don't have the useful at the moment. So take those two away. Useful is the total, take away the wasted, and we now know 400 joules is useful. Then we've just got to divide it by the 520, and we get our efficiency of 0.77. If it asks for it as a percentage, just times it by 100. Next one says an object has 1,200 joules of kinetic energy, no unit change. The mass is 5 kilograms, perfect, no unit change. Calculate the maximum velocity of the object. So we know KE equals half mv squared. I want that out of the way, so that's going to become 2KE equals mv squared. Next part, well now I want, because I'm trying to get v on its own, I want m out of the way. It's multiplied at the moment, that's going to go under here. So I'm now left with v squared equals 2k over m, and therefore v equals the square root of 2ke over m. So that's it rearranged again, or just learning. So v equals the square root of 2k over m. Well, two lots of 1,200 divided by 5, get your answer, and then square root it. So that will give us 480, and when I square root 480, I get 21.9 meters per second. Next one, why can the maximum theoretical velocity not be reached if it's falling through air? Well, the crucial part is we're going to have air resistance, we're going to have friction, and that's going to transfer some of the kinetic energy into heat. So there is air resistance as it falls. This creates thermal energy from friction, and this is dissipated into the air. So you can see that's coming up quite a few times. And that's the energy bit done.